Hi everyone, welcome back to video lecture series on RA6M5 microcontroller. In this project, I will demonstrate how to use the event link controller in RA6M5 microcontrollers. As described in the FSP documentation, the ELC is a powerful feature of RA6M5 microcontrollers that allows peripherals to communicate directly with each other without CPU intervention, improving efficiency and reducing processing overhead. As you can observe in this document, the event link controller acts like a hardware connection system that links different modules such as software events, timers, ADCs, and other peripherals, allowing them to trigger each other automatically. Normally, the CPU must handle each event using interrupts or polling, which adds delay and increases processing load. However, with the ELC, an external event or a timer overflow can directly trigger an ADC conversion without CPU intervention. This approach improves real-time performance, reduces CPU usage, and makes the system more power efficient. In this project, we will demonstrate both approaches. First, we will trigger an ADC conversion on a timer overflow without using the ELC. After that, we will use the ELC to start the ADC conversion automatically when the timer overflow occurs. Open I2 Studio, then create a new project by clicking on the file icon, then select New, then select RA6M C++ project, then select RA6M RA project. A new dialog box will appear. You can give a name to your project here. After naming your project, click on the Next button. From this drop-down menu, select the RA6M5 board. After board selection, click on Next. After that, select Flat, Non-Trust Zone Project. For Smart Bundles, select the None option, then click on Next. Now select Executable and No RTOS option. Now select Bare Metal Minimal, then click on the Finish button. Now the IDE will take some time to configure your project. Now click on the Open Perspective button to open the FSP configuration file. In FSP configuration file, click on Stack tab, then click on New Stack. Then, under Timer, select the RGPT timer stack. Click on the timer stack and open its properties. Under the General tab, you can configure the timer mode, channel, and period. For this project, I will use the default settings. Next, expand the Interrupts tab and define the callback function for the timer stack. Also, set the timer overflow interrupt priority. After this, no further changes are required with the timer stack. Now click on New Stack again. Under Analog, select the RADC stack. Click on the ADC stack and open its properties. Expand the Input tab, then expand Channel Scan Mask and select the temperature sensor. Next, scroll down and expand the Interrupts tab. Define the callback function for the ADC stack and set the scan end interrupt priority. No additional changes are required. After that, click on Generate Project Content. Expand the SRC folder and open the hallentry.c file. In the hallentry function, first I will define an FSP error variable. Then in the Project Explorer window, expand Developer Assistance and open the timer stack. From the timer stack, drag and drop the RGPT timer open function call into the hallentry.c file. After that, use the assert function to ensure that the timer open function call was successful. Next, from the Developer Assistance tab, drag and drop the ADC open function call into the hallentry.c file. And again use the assert function to confirm that the call executed successfully. Then drag and drop the ADC scan configuration function call into the hallentry.c file and use the assert function to verify its success. Afterward, add the ADC callback function to the hallentry.c file and also add the timer callback function. Inside the timer callback function, drag and drop the ADC scan start function call. When a timer overflow occurs, it will trigger the ADC scan start operation. Finally, inside the ADC callback function, drag and drop the ADC read function call to retrieve the conversion results. We can define a uint16 variable to store the ADC conversion result. In the ADC read function call, select the temperature channel and use the address of the temperature variable as the last argument. Additionally, use the FSP parameter not used function to suppress warnings related to unused parameters. After configuring both stacks in the hallentry function, drag and drop the GPT timer start function call, and then use the assert function to ensure that the timer start call was successful. Next, define an empty while one loop to keep the CPU busy. Once the coding is complete, click on your project name and select the hammer icon to build the project. After a successful build, right-click on the project name, choose Debug As, and then select Renesas GDB Hardware Debugging. Click the Switch button to open the debug perspective. In Expression window, add temperature variable and enable real-time update to monitor its value. Finally, press the Resume button to start program execution. As you can observe, the temperature variable updates with each timer overflow, confirming that the ADC conversion is being triggered correctly. In the second section of this video, I will demonstrate how to use the Event Link Controller, ELC, to trigger an ADC conversion when a timer overflow occurs. First, open the FSP configuration file. In the configuration window, click on the timer stack and open its properties. Disable the overflow, interrupt, and set the timer callback function to null to disable it. Next, open the properties for the ADC stack and select GPT timer overflow as the ADC trigger source. You will notice an error displayed on the ADC stack. If you hover your mouse over it, a pop-up window will show the error message. As shown, linking the GPT overflow event with the ADC requires an ELC stack. To resolve this, click on New Stack, then select System, and finally choose the Event Link Controller, ELC stack. After adding the ELC stack, the error related to the ADC stack will be resolved. No further changes are required in the FSP configuration file. Click on Generate Project Content, and once the content generation is complete, open the hallentry.c file. Now we can remove the timer callback function. Press Ctrl+// to perform a multi-line comment. However, for demonstration purposes, I will delete the callback function. Next, open the Developer Assistance menu and drag and drop the ELC Open function call into the hallentry.c file. After that, use the assert function to ensure that the ELC Open call was successful. Once the ELC is opened, add the ELC Enable function call from the Developer Assistance menu. Again, use the assert function to verify that the enable function executed successfully. Then drag and drop the ADC scan start function call into the hallentry.c file and use the assert function to confirm that the scan start operation was successful. With these steps, the coding part of the project is now finished. Click on your project name and select the hammer icon to build the project. After a successful build, right-click on the project name, choose Debug As, and then select Renesas GDB Hardware Debugging. Click the switch button to open the debug perspective. In debug mode, click on Rezoom button. This will reset the temperature value. Now again, click on Rezoom button. As we can observe in the expression window, temperature value is updating after each timer overflow. However, although we have disabled the timer overflow interrupt, but the event link controller is triggering the ADC conversion without CPU intervention.